Every 8 seconds, an acre of forest disappears. Ancient trees that stood for hundreds of years, gone. Meanwhile, halfway across the world, a different plant grows nearly 4 feet in a single day. While hardwood forests dwindle at alarming rates, this humble grass might just save our future. But not without controversy. When bamboo products first entered Western markets, they were heralded as the ultimate eco-friendly alternative. Yet investigations soon revealed a darker truth. Some bamboo harvesting was destroying natural habitats, workers faced dangerous conditions, and certain factories were dumping toxic chemicals into local water supplies. So is bamboo truly the green savior we need? Or just another environmental disaster wrapped in clever marketing? Today, we dive deep into the world of bamboo plywood, from humble shoot to finished product. The reality, as always, is more complex than the headlines suggest. The story of bamboo begins not in a factory, but in the misty mountains of Asia. Unlike trees that take decades to mature, bamboo reaches harvest maturity in just 3 to 5 years. But not all bamboo is created equal. For premium plywood production, harvesters specifically target Moso bamboo, a giant species that can rocket to heights of 75 feet. Timing is everything. Cut too early, before the 4-year mark, and the bamboo lacks density. Wait too long, beyond 7 years, and it becomes brittle after drying. Expert harvesters select only perfectly mature culms, the technical term for bamboo stems, measuring around 10 inches in diameter. They make diagonal cuts above the first node, preserving the root system that anchors hillsides against erosion. What few people realize is that bamboo doesn't actually die when harvested. The same root system continues producing new shoots for decades. In regions where bamboo grows on steep slopes, harvesters sometimes use specially designed pulley systems to safely lower the massive poles to collection points below. The work demands not just physical strength, but intimate knowledge of the terrain. Harvesting during the dry season reduces the bamboo's moisture content naturally, giving the material a head start on the processing journey. A single bamboo stalk can reach its full height in just 3 months, a growth rate so rapid you can actually watch it grow. The fastest recorded growth was nearly 4 feet in a 24-hour period. This explosive development requires minimal input, no pesticides, fertilizers, or irrigation systems typically needed for commercial timber. The plant's extensive root network captures and purifies groundwater, preventing erosion while improving soil quality for other species. The sustainable harvesting of bamboo has roots in ancient traditions. For millennia, Asian communities have practiced selective cutting techniques that maintain bamboo forest health. These traditional methods have inspired modern sustainable harvesting protocols that ensure continuous yields without damaging ecosystems. In contrast to clear-cutting timber operations that leave barren landscapes, properly managed bamboo forests remain visibly unchanged after harvest. Only experts can identify which culms have been removed. While the strips dry in massive kilns, let's address energy consumption. Compared to steel, concrete, or even traditional plywood, bamboo's footprint remains remarkably small. Modern factories increasingly use solar panels and burn bamboo waste to power their operations, further reducing environmental impact. The drying phase represents perhaps the most critical and delicate stage in bamboo plywood production. The moisture content must be reduced from as high as 50% to precisely 8 to 10%, a narrow window that requires expert monitoring. Too dry and the bamboo becomes brittle. Too wet and it warps later. Advanced factories employ computerized kiln systems that adjust temperature and humidity in real time based on continuous moisture readings from sensors embedded within sample strips. What's fascinating is how this modern technology often combines with traditional knowledge. In some regions, master craftspeople still perform what locals call the bamboo whisper test, listening to the sound bamboo makes when struck lightly at different stages of drying. These experts can detect subtle variations that even sophisticated moisture meters sometimes miss, ensuring optimal drying without damage to the cellular structure that provides bamboo's legendary strength. Once dried to precisely 8 to 10% moisture content, the strips move to the selection room. Here, human eyes still outperform machines. Workers rapidly sort strips by color, density, and grain pattern. The finest strips destined for premium plywood undergo one more specialized treatment depending on the desired end result. For the increasingly popular carbonized look with its rich amber tones, the strips are steam heated in pressure chambers. This process caramelizes the natural sugars remaining in the bamboo, darkening the color without any chemical dyes. An unexpected detail: the timing of the harvest drastically affects the final color. Bamboo harvested just after the rainy season contains more starches that caramelize more intensely during carbonization, producing deeper amber tones. Some premium manufacturers actually schedule different harvests throughout the year to achieve specific color ranges, much like vintners harvesting grapes at different times for various wine profiles. Now comes the transformation from strip to sheet, the heart of plywood production. Factory workers arrange strips in various patterns, creating different aesthetic and structural properties. In horizontal grain plywood, strips lay parallel to each other, creating a clean, contemporary look. Vertical grain arrangements, where strips stand on edge, provide maximum strength for structural applications. The most distinctive option, strand-woven bamboo, involves shredding strips into fibers, mixing them with adhesive, and compressing them under extreme pressure to create densities even harder than oak. Speaking of adhesives, this represents the most significant environmental challenge in bamboo plywood production. Traditional plywood often uses formaldehyde-based glues that continue off-gassing toxins for years. Progressive bamboo manufacturers have pioneered plant-based and water-soluble alternatives that dramatically reduce both environmental impact and health concerns. A fascinating innovation comes from research inspired by mussels, those small shellfish that cling to rocks in crashing waves. Scientists studying the natural adhesive mussels produce have developed biomimetic bamboo adhesives that bond underwater and contain zero toxic components. This technology represents the cutting edge of truly sustainable manufacturing. The arranged strips then enter massive hydraulic presses, where temperatures reach 230 degrees Fahrenheit. Under pressures exceeding 3,500 pounds per square inch, the strips and adhesive fuse into solid panels. The precision this requires is extraordinary. Vary the temperature by just a few degrees, or the pressure by a small percentage, and the entire batch might be compromised. One remarkable aspect of bamboo plywood production is the layering process. For 3-layer plywood of standard 3/4 inch thickness, manufacturers don't simply press everything at once. Instead, they create a carefully orchestrated sequence, first pressing surface and bottom layers, then preparing the core layer, and finally joining all three together. Between these pressing stages, workers sand each component to microscopic smoothness, sometimes achieving surface variations of less than 0.001 inches. This meticulous attention explains why quality bamboo plywood remains perfectly flat for decades, while cheaper alternatives often warp within months. After the final pressing, the panels require cooling under continued pressure. Some manufacturers employ water-cooled press plates to accelerate this process, reducing both energy consumption and production time. The craft element of bamboo plywood production often goes unnoticed. Despite advancements in automation, the most critical quality decisions still rely on human expertise. Master craftspeople with decades of experience can detect subtle issues by sound alone, tapping finished panels and identifying internal delamination that even ultrasonic testing might miss. This combination of advanced technology and traditional craftsmanship creates products that neither approach could achieve alone. The internal structure of premium bamboo plywood reveals design ingenuity that goes far beyond simple layering. Engineers have developed gradient density panels where the outermost layers utilize dense, carbonized bamboo for wear, resistance, and aesthetic appeal, while inner layers incorporate lighter, more flexible bamboo varieties that provide shock absorption and reduce overall weight. This biomimetic approach mirrors natural structures like bone, which feature dense exterior shells surrounding more flexible cellular interiors. The near-final panels now move to trimming stations, where computer-controlled saws cut them to standard dimensions, typically 4 feet by 8 feet. The precision of these cuts matters tremendously. Panels just a fraction of an inch too small create installation nightmares, while oversized panels waste material and cause fitting problems. The best facilities collect every scrap, processing smaller pieces into edge banding and furniture components. The smallest fragments and sawdust become either fuel for the factory's boilers or raw material for bamboo fiber composites. After trimming comes the crucial finishing stage. Workers meticulously sand both surfaces to their final smoothness, progressing through increasingly fine abrasives. The finest bamboo plywood passes through up to 9 sanding stages, creating surfaces so smooth they feel almost like satin to the touch. One unique aspect of bamboo finishing involves specialized ultraviolet cured coatings that penetrate deep into the material's surface. Unlike traditional film-forming finishes that sit atop the wood, these modern coatings bond at the molecular level, creating wear resistance that far exceeds conventional treatments. In commercial applications, this translates to flooring that maintains its appearance for decades rather than years. Many manufacturers apply protective finishes at this stage, ranging from simple UV protective coatings to specialized finishes for marine applications. An interesting fact: bamboo plywood with proper marine finishes outlasts many hardwoods in saltwater environments, resisting the barnacles and marine borers that quickly destroy other materials. Some manufacturers have developed specialized nano-coatings that actually harness bamboo's natural antimicrobial properties. By extracting and concentrating compounds naturally present in bamboo, these finishes create surfaces that actively inhibit bacterial growth, a particularly valuable feature in healthcare settings, restaurant kitchens, and other environments where hygiene is paramount. Unlike conventional antimicrobial treatments that rely on potentially harmful chemicals, these bamboo-derived solutions operate through entirely natural mechanisms. The finished plywood now undergoes rigorous testing. Beyond standard structural tests measuring strength and flexibility, manufacturers increasingly perform environmental assessments that verify the finished product contains no harmful chemicals. The most stringent testing comes from international certification programs. These evaluate not just the final product, but the entire supply chain, from sustainable harvesting practices to worker safety and environmental impact. The gold standard, FSC certification, ensures the bamboo comes from sustainably managed forests while meeting strict social and environmental criteria. Few consumers realize the breadth of testing modern bamboo plywood undergoes. Beyond structural integrity, panels face simulated aging tests that compress decades of environmental exposure into weeks through extreme temperature cycling, humidity fluctuations, and ultraviolet bombardment. Only products that emerge from this gauntlet unchanged receive premium certification. The testing protocols reveal bamboo's extraordinary durability. In standardized abrasion testing, where surfaces are subjected to thousands of passes with sandpaper under consistent pressure, quality bamboo plywood typically outperforms oak by 25 to 30%. This explains why bamboo flooring maintains its appearance in high-traffic commercial settings where conventional hardwoods would show significant wear within years. After passing inspection, the panels are carefully packaged for shipping. Unlike many wood products that can be stacked directly, bamboo plywood requires protective wrapping to prevent moisture damage during transport. The best manufacturers use biodegradable wrappings rather than plastic films, further reducing environmental impact. What truly sets bamboo plywood apart is its exceptional performance in specialized applications. The material's natural resistance to humidity changes makes it ideal for spaces with extreme moisture fluctuations, from bathrooms to outdoor structures. In Shanghai, engineers constructed a pedestrian bridge using bamboo plywood components that outperformed steel in both tensile strength and corrosion resistance. After 5 years in the humid coastal environment, the bamboo elements showed virtually no degradation, while comparable metal components required replacement. The thermal properties of bamboo plywood have led to its use in passive solar building designs. The material's unique cellular structure provides natural insulation, while its thermal mass helps regulate indoor temperatures. In desert climates, buildings incorporating bamboo plywood walls have demonstrated up to 40% lower energy consumption for cooling compared to conventional construction. Acoustical engineers have embraced bamboo for its sound absorption characteristics. Concert halls in Japan, China, and increasingly in Europe incorporate bamboo panels specifically designed to diffuse and enhance sound. These specialized panels feature micro-perforations that trap specific sound frequencies while allowing others to pass through, creating acoustic environments that would require much more complex and expensive solutions with conventional materials. In Vancouver, architects designed the world's first bamboo plywood skyscraper, an 18-story wonder that sequesters more carbon than was emitted during its construction. In Japan, furniture makers create pieces so beautiful they're exhibited in museums, showcasing intricate joinery techniques specifically adapted for bamboo's unique properties. The medical applications of bamboo might be its most surprising frontier. Researchers have developed bamboo-derived scaffolding for tissue engineering that outperforms synthetic alternatives. The natural microchannel structure of bamboo fibers provides ideal pathways for cellular growth, while compounds naturally present in bamboo demonstrate antimicrobial properties that reduce infection risk. Even NASA has taken notice, experimenting with bamboo composites for spacecraft components due to their exceptional strength-to-weight ratio and natural radiation shielding properties. The material's ability to dampen vibrations makes it particularly valuable for sensitive equipment housings, while its natural thermal insulation properties help maintain stable temperatures in the extreme environment of space. Perhaps most remarkable is bamboo plywood's performance in earthquake zones. Its natural flexibility allows structures to bend rather than break during seismic events. After the devastating 2015 Nepal earthquake, engineers discovered that properly constructed bamboo buildings suffered significantly less damage than concrete structures, leading to new building codes that specifically address bamboo construction methods. The combination of traditional wisdom and modern science has created bamboo building systems that specifically address the challenges of disaster-prone regions. These systems utilize bamboo plywood's flexibility and tensile strength while addressing its traditional weaknesses through modern treatments and engineering. The result: affordable housing solutions that survive earthquakes, typhoons, and floods that demolish conventional structures. Of course, no material is perfect. Bamboo plywood faces legitimate challenges that rarely make headlines. Despite its tremendous growth rate, global demand now threatens to outpace sustainable production. Some regions have converted diverse natural forests to bamboo monocultures, an environmental catastrophe masquerading as green progress. These plantations support a fraction of the biodiversity found in natural forests while depleting soil nutrients at alarming rates. Transportation represents another challenge. Most bamboo still grows in Asia, while many consumers live in North America and Europe. The carbon footprint of shipping heavy materials thousands of miles partially offsets the environmental benefits of choosing bamboo over local alternatives. Quality control issues also plague the industry. Without unified global standards, some manufacturers cut corners by using harmful adhesives or harvesting immature bamboo. These inferior products fail prematurely, unfairly tarnishing bamboo's reputation. Yet solutions are emerging. Bamboo cultivation has successfully expanded to new regions, including parts of North America, reducing transportation distances. DNA fingerprinting technology now allows distributors to verify the exact species and age of bamboo used in products they import, ensuring only mature, appropriate varieties enter the supply chain. International certification programs are establishing consistent standards across the industry. Perhaps the most exciting developments lie in bamboo's future. Researchers have developed methods to create transparent bamboo, yes, transparent, by removing specific cellular components while preserving structural integrity. The resulting material offers the strength of bamboo with the light transmission of glass. The integration of bamboo into sophisticated composite materials represents another frontier. By combining bamboo fibers with biodegradable polymers, engineers have created materials that approach the performance of carbon fiber composites while remaining environmentally benign throughout their life cycle. These materials have found applications in everything from automotive components to consumer electronics housings. Nanotechnology offers another frontier. By extracting nanocrystals from bamboo fibers, researchers have created supermaterials with applications in everything from medical implants to ballistic armor. These nanocrystals provide strength comparable to carbon fiber, but from a renewable resource that requires minimal processing. Even bamboo waste is finding new life. Researchers have developed methods to convert processing byproducts into activated carbon for water filtration, addressing clean water challenges in developing regions while creating additional value from what was once considered waste. The development of self-healing bamboo composites represents perhaps the most futuristic application. By incorporating microcapsules of bamboo-derived adhesives within plywood structures, engineers have created materials that automatically repair minor damage. When microcracks form, these capsules rupture and release adhesive that polymerizes on contact with air, effectively healing the damage before it can propagate further. The economic impact of bamboo plywood extends far beyond manufacturing profits. In rural Asian communities, bamboo cultivation provides sustainable livelihoods that allow families to escape poverty while preserving traditional agricultural practices. Unlike many cash crops that require clearing forests, bamboo thrives in mixed agroforestry systems that maintain biodiversity and ecological balance. Community-owned processing facilities have emerged as a model for equitable development. Rather than shipping raw materials to distant factories, these operations produce value-added bamboo products locally, keeping economic benefits within communities. Some cooperatives now produce bamboo plywood that carries both environmental and fair trade certifications, ensuring both ecological and social responsibility. Educational initiatives focused on bamboo construction have created new generations of architects, engineers, and builders specializing in this material. Universities in Colombia, China, Indonesia, and increasingly in Europe and North America now offer specialized courses in bamboo architecture and engineering. These programs are creating professionals who understand both bamboo's traditional applications and its potential for innovative modern construction. The insurance industry has taken notice of bamboo's resilience. In regions prone to natural disasters, structures utilizing bamboo plywood and engineered bamboo components increasingly qualify for reduced premiums due to their demonstrated ability to withstand extreme events. This economic incentive is accelerating adoption of bamboo construction methods, particularly in coastal and seismic zones. Bamboo plywood stands at a crossroads. When responsibly sourced and manufactured, it offers exceptional performance while protecting our forests. But these benefits vanish when corners are cut. The choice is ours. By demanding transparency and proper certification, we shape the industry's future. From humble grass to high-performance building material, bamboo represents the kind of innovative thinking our planet needs. If you found this journey valuable, hit subscribe for more deep dives into tomorrow's materials. Share with friends interested in sustainable design. Together, we can build a better future. Until next time, remember, nature's most extraordinary solutions often grow right beneath our feet.